All right. So welcome to lecture 3 on the tree abstract data type. And in today's lecture, we are going to look at a whole sequence of formulae that one can write down on a binary tree. And each of these formulae are very important, and these are formulae for which you should write functions using the binary tree ADT and the tree ADT that we have defined and implemented in the previous lectures. In today's lecture, you will not see any C program that I have written, but a complete analysis of the different formulae that we want to write associated with binary trees. And you will also see some of the examples that were hard coded into the C programs in today's lecture in the slides. So today is essentially going to be a presentation based on slides, and there will not be any C program. All right, let's go to the slides and move on with a study of applications using the tree ADT. In particular, we will be using binary trees, and let us look at the in-memory visualization of a tree. Right, this is a node. It has three pointer fields: the left pointer to the left child, the pointer to the right child, the pointer to the parent, and the field that contains the data value. And this is the abstract view of this picture, that this is the node that contains B. The left child of this node is a node that contains A, which is the leaf node. Right? And the right child of the node that contains B is the node that contains D, which is not a leaf node, it's an internal node. And this, as you can see, is a binary tree in which every node has two children. Every internal node has two children, and every external node by definition has 0 children. Okay, let's look at an arithmetic expression tree. Okay. So therefore, observe that this tree, this binary tree is used to store an arithmetic expression. Okay. So now, most of us are familiar with this way of writing an arithmetic expression, but inbuilt into this way of writing the arithmetic expression and the way in which we evaluate it is actually a binary tree. Okay. So observe that this binary tree encodes this arithmetic expression. So let us look at another application of the binary tree. You can think of this as a data structure which can store decision trees. Right? So what is a decision tree? This is essentially a tree that helps you get answers through a sequence of questions. Right? So let us consider a sequence of questions. Do you want to become famous as a technologist? If your answer is do you want a PhD? If your answer to that question is a yes, then you can register for a PhD at an IIT or at one of the research labs. Okay? And if you don't want a PhD, okay, then you want a startup. So if you want a technology fame, then if you want a PhD, that's the answer is yes to that question, then you can either do a PhD at an IIT, and if the answer to that is a no, then you would want to do a PhD at a research lab. And if you don't want a PhD but you want tech fame, then maybe you want a startup. And if you want a startup, do you want a tech startup? And if it is yes to a tech startup, you can go on and create a tech startup. And if it is not a tech startup, do you want a service startup? So this is an example in career decision. So therefore, binary trees can be used to encode decisions that are made. I mean, so one can modify this image and one can put in all kinds of other decisions that you would want to take. So let us look at some parameters associated with a binary tree. So for example, how many nodes, what is the maximum number of nodes which are possible in a binary tree? The answer is very simple. It is the maximum number of nodes in a binary tree of the maximum number of nodes in a binary tree of height k is obtained by adding up the total number of nodes which are available at each level I. So at a depth I, the total number of nodes that are possible is 2 to the power of I for I greater than or equal to 0. That is, at the root node there is only one node. At depth 1 there can be at most 2 nodes. At depth 2 there can be at most 4 nodes. And if you add up the whole lot of them, then you essentially get 2 power k plus 1 minus 1. This really does not require any proof by induction, though I have written a proof by induction. You can definitely write a proof by induction if you want to. How many nodes are there in a full binary tree? Right? A full binary tree is a tree, right, which has all its nodes, right? And as we have seen in the previous slide, this is 2 power k plus 1 minus 1, where k is the height of the tree. That is, this is at depth 0, this is at depth 1, depth 2, and depth 3. This is a binary tree, a full binary tree of height 3, and you can actually verify that the total number of nodes which are there are 15 of them. So you will see 8 here, plus 4, 12 here, plus 3, 15 nodes. How does one label the nodes in the full binary tree? And this is extremely important. And in this slide, I would encourage the listeners or the readers to actually not confuse the data item which is typically stored inside a node with the label. Right? In this case, this node has label 1, this has label 2, label 3, and so on. And the way we do it is to use increasing order of labels as we go from top to bottom, that is from the depth 0 onwards to the maximum depth. And inside a layer, we use increasing order of distinct labels from left to right. So now observe that the order is very important. For example, the left child of 1 is 2. Left child of this node is a node labeled 2, and the left child of the right child of this node labeled 1 is the node labeled 3, and so on and so forth. Therefore, you can see that the labels are 1, 2, 3, 4, 5, and the interesting thing is that if you did a pre-order traversal, you have some very special properties if you did a pre-order traversal. Let us look at what the special properties are. So now let's look at the properties of the node numbering scheme. Right? So for example, the parent of a node I gets the label I divided by 2 unless I is equal to 1. Right? And there must have been a ceiling here. This is the integer division. So I take recourse to the C programming language. Right? So the parent of the node 2 is 1, parent of the node 3 is 3 by 2. This is the integer division in C, and that is also a value 1. Same is true with every node. And if you want to know what the child of the node 3 is, the left child of the node 3 has the label 6, right? And in this example, right, the left child of the node 15, right, should have been 30, but that label is more than the total number of nodes in the tree, right? And therefore the left child of node I is 2i unless 2i is more than n. In this case 30 would be more than 15, and therefore the left child is not well defined. If 2i is more than n, then I has no left child, as in the example of 15, 14, all the way up to 8. Same with the right child. The right child of the node I is 2i plus 1 unless 2i plus 1 is more than n. In other words, for any number which is greater than or equal to 8, there is no right child. And this is encoded in these labeling schemes. One major application of these node numbering properties is that these give you a convention of storing a binary tree in an array. Right? Especially if you want to represent a complete binary tree in an array, the root can be stored at the first element, the left child of the root can be stored at the second node in the array, and the right child of the root can be stored at the third element of the array. The fourth element of the array contains the left child of the element in the second element of the array, second location in the array, and the fifth location of the array contains the right child of the element in the second location of the array. Right? Observe that the most important thing here is that the root must be given the label of 1. This is a very crucial thing. Therefore, observe that this way of labeling, right, which we have studied in the last couple of slides, is not a very not a trivial, useless kind of a labeling. It's very important. If you wanted to implement a binary tree in an array, then you know exactly where, in which locations the specific nodes have to sit. Right? And we also have a convention that such a tree is a complete binary tree. That is, a complete binary tree, right, is one in which all the nodes at a particular level have the labels which are in increasing order from the smallest label available for that particular level. Right? That is, the binary tree with n nodes and level k is complete if and only if all the nodes correspond to the numbers from 1 to n in the full binary tree up to level k. Right? Observe that if you had taken the nodes 8 and 9 and made them children of the node 5, then you would have not had a complete binary tree. This is the most important thing. You take a full binary tree and eliminate some of the nodes which have the largest labels, right, consecutive ones, that is from 12 to 15, you remove all of them, then you get a full binary tree, right, with 11 nodes in it. If you eliminate all the nodes labeled 8 to 15, then you get a full binary tree of depth 2 now, and so on and so forth. Right? So note the difference between a complete binary tree and a full binary tree, and specifically note, importantly, the definition of a complete binary tree. This way of viewing complete binary tree and full binary tree immediately suggests to us a very natural implementation of a complete binary tree in an array. The most important thing is that the root element of the complete binary tree is stored at index 1 in the array, and the remaining elements are stored at appropriate multiples. Right? For example, the location 2 contains, the index 2 contains a left child of the root element, the location 3 contains the right child of the root element, and so on. Let us look at the exercise of printing arithmetic expressions. Right? So what we do is that we follow the following simple rule, that we place a parenthesis, right, just before traversing the left subtree, and print a close parenthesis after traversing the right subtree, and print the elements in order. Then we will be able to print the expression exactly in the order in which we would want to implement it using the board mass rules. Right? So let us just try this. So I put an open parenthesis here, I put another open parenthesis here, then I print 2, then I print star, that is to print this one. Now I put an open parenthesis here, print a, print the -1, print 1, then close the parenthesis, then close the parenthesis, right? Then I go here, right? Sorry, print plus, right? Then go to the right child and recurse. Then observe that the expression is printed exactly in the order in which I would want it to be evaluated. That is, the innermost parenthesis gets evaluated first, okay? Then among the available innermost parentheses, the one left gets evaluated, the multiplication is done, then this parenthesis gets evaluated, the result is added, and that is considered to be the value printed by the tree. That is for expression evaluation, but this is for printing the expression. How does one evaluate this arithmetic expression? Exactly as we did just now. So you evaluate the left child, you evaluate the right child, you pick up the operator, return the results of the left child and right child evaluation, and print out the value. Here is the last application. Right? It's called the path length of the tree. The path length of the tree is very important in understanding, say for example, how much of wire is required to represent this particular tree if you view it as a Boolean circuit. Right? So the path length of the tree is essentially the sum of the different depths. This is the definition. Right? So you look at all the nodes, right? look at the depth of every node and add up all the depths. We define this as the path length of the tree. It's very easily defined as a recursive function. Right? Let us just take a look at this. If it is an external node, right, and if you are doing a path length on a tree with depth n, and if the node is at depth n, then you return the value of the depth. The usage is that the function gets called with the root node given the value 0. If it is not an external node, we return the value which is the path length from the left child at n plus 1 plus path length of the right child at n plus 1 plus n. Right? This whole thing is evaluated first, and then a value of n is added to it. Right? That is, n is the value of the parent also. So it is an important exercise for you to now check that this implementation of path length exactly computes the sum of the depths. That is the exercise. So let us see. We want to write a recursive function. This function is called path length, and the result of this path length when called at the root with an initial value 0 is that it must return the sum of all the depths. Right? And the rule is very simple. If it is a leaf node, you return the depth value itself, and if it is not a leaf node, you go to the left child, increase the depth value to n plus 1, go to the right child, increase the value to depth plus 1, compute the path lengths there, then add the path length value n and return the value. With a pen and paper exercise, you can very easily check that this indeed returns the sum of the depths of all the nodes in the tree. However, I encourage you to write this as a recursive function in C and check that it works. Alright, so this brings to an end this set of 3 lectures on the tree abstract data type, and this is our first exposure in this course to a nonlinear data structure. Observe that all the concepts that we have studied in the earlier data types are also implicitly used. For example, when we use recursion, you are using a stack. When you maintain the leftmost child right sibling notation, remember that we are maintaining a doubly linked list. Right? And when you traverse these nodes, when you perform a traversal, let us say a post order or a pre-order traversal of a tree, then the children are traversed in a queue-like order in the order in which the data is represented in memory. Therefore, the algorithmic methods associated with the tree abstract data type and the binary tree data type implicitly have used all the methods that we have studied with the other data types. Right? And you can observe that the purposes of a binary tree and a tree in general, right, are many. A binary tree, for example, is an ordered tree. You can represent arithmetic expressions using a binary tree because of the fact that it is an ordered tree, and you can evaluate these expressions in the appropriate way following the Bodmas rules and get consistent answers. So the tree abstract data type is an extremely important concept that you have learned over this week. In the next week, we will see how to augment additional properties of the data onto the binary tree and implement what are called binary search trees and heaps. And using heaps, we will implement priority queues. Remember that we studied queues a few lectures back. So that brings to an end this set of lectures for this week, and when we meet next, we will be studying more sophisticated data structures and their implementations. Thank you. Hope you enjoyed these lectures.